Welcome to the deep dive. Today, we're going to tear open the architecture of these huge large language models, the AIs we all interact with every day. And we're going to look at this fundamental performance strain that's happening right under the hood.
It's one of the great ironies of modern AI, isn't it? You have these massive systems with trillions of parameters that can write poetry or draft legal briefs.
Right.
And yet they really struggle with a task that, any simple database could do in an instant. And that's just looking up a known fact.
I find this so baffling because if you ask an LLM who won the 1998 World Series, it knows the answer, but it's how it gets to that answer that's the problem. Our source for today puts it really clearly. These models lack a native primitive for knowledge lookup.
They do. They're forced to inefficiently simulate retrieval.
Yep.
So think of it this way. Instead of just walking over to a filing cabinet to pull out a memo, the LLM has to use its entire, high-powered brain to reconstruct that memo from scratch.
Every single time.
Every single time the fact is needed. And it's just this massive waste of computation.
Computation that, as you said, should be for actual, novel reasoning, not just recalling stuff we already know.
Exactly. That overhead is really the enemy when you're trying to scale these things efficiently.
So our mission for this deep dive is to unpack a really elegant architectural solution for this. It's called conditional memory via scalable lookup. The researchers built a module for it called Engram, and the results, well, they don't just improve fact recall, they get these massive and honestly really unexpected gains in complex reasoning.
So let's start with where this even fits in. We talk a lot about scaling AI, about making models bigger and smarter, usually through things like sparsity.
Right. And sparsity just means you're not firing up the whole brain for every single task. The big method right now is mixture of experts, or MOE. And this paper frames Engram as introducing a completely, what they call a complementary sparsity axis.
That phrase is so important. A complementary sparsity axis. See, MOE scales up its power using conditional computation. It's basically asking, okay, for this specific problem, which expert part of my neural network should I turn on?
And that's a huge efficiency win.
A huge win. But conditional memory is different. It's not about which part computes. It's about whether to compute at all.
It just takes the knowledge out of the calculation process entirely.
Exactly. Engram scales capacity using static, scalable lookup. It's physically pulling the knowledge storage out of the neural network's main path. And this isn't just, sticking a database on the side. It's deeply integrated.
So what's the magic here? What makes it so fast? They talk about modernizing Engram embedding, but the real breakthrough seems to be this constant time lookup.
That's the holy grail of efficiency right there. O1 lookup. And just to stress how big a deal this is, with most retrieval methods, the bigger your knowledge base gets, the slower the search becomes. Maybe it's logarithmic, maybe it's linear.
Right, it takes longer to find a book in a bigger library.
But O1 means the time is constant. It doesn't matter if you have 10,000 facts or 10 billion. The lookup is instant.
That is just a staggering improvement. So for you, the listener, this means the model doesn't have to burn its precious computational power, its neural layers, its attention, just to figure out the capital of France. That fact is just shunted off to a super fast memory bank.
Which frees up all the heavy machinery for the real job. Synthesis, structure, reasoning.
Okay, so this brings us to the theory behind it. They didn't just stumble on this. They formulated this whole problem they call the sparsity allocation problem.
Right, and the question is pretty simple but profound. It's, if you have a fixed budget of parameters, of electricity, how do you split your resources between the thinking part, the neural net, and the memory part, the Engram?
And the solution they found is what's really fascinating. It's a U-shaped scaling law. I think most of us assume scaling is just a line going up. More is always better. A U-shape implies a sweet spot.
It absolutely does. That U-curve is the guide to optimizing the trade-off between neural computation, for the MOE part, and static memory from Engram. If you're too far to the left of the U,
you have too much brain, not enough memory.
Exactly. Your model is powerful, but it's wasting all its energy just trying to remember things. It's inefficient.
And too far to the right.
Too much memory, not enough brain. You can look up facts instantly, but you don't have enough computational horsepower to do anything smart with them. The bottom of that U, that's the perfect balance.
And they didn't just theorize about this, they went big. They scaled an Engram model up to 27 billion parameters. So this is not just some academic thought experiment.
Whoa, this is a real blueprint for how to build next-gen models. And the results prove the theory right. They built a control model, a standard MOE model, with the exact same parameter count and the same computational budget, same FLOPs.
A completely fair fight.
A totally fair fight. And the Engram model achieved superior performance. It was just flat out better.
So that's the clearest evidence you could get. It's not just an add-on, it's a fundamentally more efficient architecture.
It completely changes the equation.
Okay, let's unpack this, because this is where the results get really, really interesting, and frankly, a little weird.
Right.
You build a memory module, you expect it to be good at memory tasks, and it was.
Oh, yeah, they saw great results. On a benchmark like MMLU, which is a huge test of knowledge across dozens of subjects, they saw a gain of plus 3.4 points. For the Chinese version, CMMLU, it was plus 4.0. I mean, those are solid gains.
Makes perfect sense. Better memory scores.
Yeah.
But what about reasoning?
This is the surprise. This is the big reveal. They found even larger improvements on tasks that have nothing to do with simple fact recall. Tasks that require logic, synthesis, multi-step reasoning.
Wait, you're telling me that giving the model a better address book makes it better at writing code and solving logic puzzles? That just does not compute for me, intuitively.
I know, it feels wrong, but the data is right there. On a benchmark called Big Bench Hard, BDH, which is designed specifically to torture models with hard, multi-step reasoning, they saw a gain of plus 5.0.
5 points. On a hard reasoning test? That's huge.
It's massive. And it wasn't a fluke. On ARC Challenge, which is all about common sense reasoning, plus 3.7. And it even extended into these really specialized domains.
Like programming and math.
Exactly. On Human Eval, for code generation, a plus 3.0 gain. For the math benchmark, solving math problems, plus 2.4. The fact that a memory module helps you solve a geometry proof is, well, it's the central mystery here.
Which leads to the big question they had to answer. Why? What is the mechanism that's driving these incredible and totally unexpected gains in reasoning?
So they did a deep mechanistic analysis, and the core insight is that Engram just fundamentally changes how the LLM distributes its workload, specifically in the first few layers of the transformer.
So it's not just adding something, it's optimizing how the whole system works.
It's a smart reallocation of resources. Think about it. Because Engram is handling all the boring lookup work, it relieves the backbone's early layers from static reconstruction.
Ah, okay.
Those first few layers, which would normally be busy just trying to figure out the basic facts in the prompt, are suddenly free.
I love that. It's like if the first few cores of your computer's CPU were always maxed out just loading the operating system files, you'd have less power for running an actual program.
That's the perfect analogy. By offloading that basic work to Engram, you effectively deepen the network for complex reasoning. Layer 1 can immediately start working on the deep logical structure of the problem, not just figuring out what a word means.
You're getting the full power of the network on the actual hard problem right from the start.
And this has a second massive effect on the model's attention. By delegating all those little local lookups, Engram frees up attention capacity for global context.
So because the model isn't squinting at the details, it can zoom out and see the big picture. The whole argument, the long-range connections in the text.
And we have hard proof of this. They tested it on a benchmark called multi-query NIAH, which is brutal. It forces the model to find tiny critical details scattered across a really, really long document.
That sounds like a perfect test for global attention, so what happened?
The numbers are incredible. The score jumped from 84.2 all the way to 97.0.
Wow, a nearly 13-point jump.
I mean, that's about as definitive as it gets. It proves the model's attention isn't getting bogged down in local details anymore. It can hold the entire complex context in its head.
So this is really an architectural fix. It's letting the transformer finally do what it was always meant to do. You're clearing the traffic so the race car can actually race.
Exactly. It resolves a deep internal inefficiency.
Okay, let's switch gears to the engineering side. Because for our listeners, the big question is always, is this practical? How do they actually achieve this infrastructure-aware efficiency?
It really all comes down to one key detail: deterministic addressing.
Meaning what, exactly?
It means the system knows the exact location of every single piece of knowledge in the memory bank ahead of time. There's no searching, no guessing. It's a known address.
And why is knowing that address so critical for the actual hardware, for the infrastructure?
Because it enables prefetching. The system can look ahead just a few milliseconds and predict which facts the neural network is about to need. And because it knows the exact addresses, the hardware can start pulling that data from memory into the super-fast cache before the computation even asks for it.
So it's loading the data predictively.
Yeah.
The information is already there, waiting the instant the model needs it. There's no latency, no waiting time.
That's the genius of it. The authors measured the actual system overhead from all this prefetching, and they found it was negligible.
Negligible.
To get this massive performance boost, this huge memory capacity, and you don't pay a real speed penalty on the hardware. That is the definition of efficiency.
And that's what makes something go from a clever lab experiment to an indispensable part of the architecture.
It just changes the cost-benefit analysis. Storing knowledge in cheap memory is way more efficient than storing it in expensive computational units.
So wrapping this all up, what does this mean for the future of AI design? The researchers seem to have a pretty clear vision. They say they envision conditional memory as an indispensable modeling primitive for next-generation sparse models.
And they should. I think this represents a pivotal, maybe even overdue shift in architecture. We're finally moving away from forcing the computational engine to pretend it's a memory drive.
Right.
And we're moving toward implementing genuine constant time O1 knowledge lookup.
And because of that U-shaped scaling law, it's not just about mindlessly throwing more compute at a problem anymore. Future models are going to be about that strategic balance, the trade-off between computation from MoE and static memory from Engram.
And that optimization has been proven now to unlock better performance everywhere, but especially in these high-value areas like math, coding, and complex logical reasoning.
So here's the final provocative thought I want to leave you with, and it builds on that brilliant infrastructure design you just described. The paper says Engram's deterministic addressing allows for prefetching with negligible overhead. So, if that's true, the practical limit on how much external knowledge you can plug in has kind of been removed. So if you can externalize all essential static knowledge and you can access it instantly without slowing down the core reasoning engine, what becomes the new bottleneck? What is the new fundamental limit for how large and knowledgeable an LLM can ultimately be?
If speed isn't the limit, and memory capacity is practically infinite.
Yeah.
That's the question that's going to drive the next 10 years of this field. Thank you for diving deep with us.
We'll see you next time on The Deep Dive.